today he will share with us one of his research topics, and he will talk about basically, or he will tell us an introduction to general symmetries, generalized symmetries. So with that, I will give it so another round of applause. Thank you.
Thank you very much for the kind introduction, and thank you very much for the invitation to give a presentation here. It's a wonderful university, and I've never been here before. It's really impressive. Also, to be honest, I was expecting this to be a more informal discussion type seminar. I'll try to improvise, and so please just consider this as a very informal seminar. So if you have any questions at any moment, please ask. And my goal was basically to give a very elementary or first introduction to generalized symmetry. And my goal is not necessarily to describe some very recent results or some research problems, but really to give an idea about what this topic is and where it came from or why we kind of care about this kind of things. So the most important thing is that you all at least get the basic ideas. So again, please ask questions. By the way, are you guys familiar with this term, generalized symmetry? Okay, yeah, that's fine. So okay, let's see. So maybe at the end of the day, I want to say something like, say 40 Young-Mills theory has a U1 cross U1 one-form symmetry. Okay, yeah, so for example, right now, does this sentence make sense to you, or is it completely new? Well, so if it is completely new, then yeah, the goal would be that maybe at the end of the talk, you have some idea of what these terms mean and why this is a valid state. Okay? So as long as you kind of get that, it's yeah. So before talking about generalized symmetry, let's make sure that we're on the same page about what we mean by symmetry. So what is a symmetry? I assume that most of you will be familiar with some notion of symmetry. So I am going to talk about symmetry in quantum field theories. Let's see. An extremely elementary example of what I mean by symmetry is something like the following. So you can write down a Lagrangian of free complex scalar fields, right? So phi and phi bar are complex scalars. And this Lagrangian has the following symmetry, that you can transform your fields. So you can multiply your fields by an arbitrary phase. And Lagrangian does not change. So this is kind of what I mean by an ordinary symmetry. You may also be familiar that this symmetry comes with the conserved current, which, say, in this case is something like the following. And so this is the Noether's current. And Noether's theorem tells you that the fact that this Lagrangian has this symmetry means that this current is conserved. This simply means this is 0. And this, of course, follows from the equations of motions of this theory. Any questions so far? Anything unfamiliar? If any notation, because notation may be new, right? Because different people use different notation. So if any notation is unfamiliar, then please ask, because I will keep using it. Okay, great. So what we say here is that, so this theory has a U1 symmetry. And if you take any random element from U1, so just a phase, e to the power I alpha, then you can act on the operators of your theory with this group element, and they will transform it in a certain way. So we have established that the fundamental fields of the theory are phi and phi bar. So any composite fields you can build out of these things. For example, you can take, say, phi to the power k. So this is a field. You can also think of it as an operator. So this operator is going to transform under the action of this group element, right? So let's say, so how does this group element act on this operator? So the action is going to be that, so this is going to be mapped to, I will draw a picture first. So let's say this is my operator. I didn't specify this best, but it doesn't matter at the moment, but you can think of it as, let's say, in 4 dimensions. Let's say. Oh, that is the action. Now, the picture that I'm going to draw is that, so you put an operator at a particular point in your spacetime, and then you surround this operator by a closed sphere, or a topological sphere. So in this case, it's going to be a topological S3. And on this S3, you have an integration of your current. Okay. So is this construction clear? Or yeah, please ask if anything is unclear. So what I really mean is that, so in 4-dimensional spacetime, you have a point where we have this operator phi to the power k, and you enclose this point by topological S3. So for example, if you were in 2 dimension, then you would draw a point, and then the circle would be a topological S1. By topological, I mean that it doesn't really have to be completely spherical. You can deform it as long as it's smoothly deformable to S3. It counts. Yeah, so if you were in 2 dimension, then you would surround a point by a circle. If you were in 3 dimension, you would surround a point by a 2-sphere, and in 4 dimension, it's a 2-sphere. Yes. Right. Yeah, so let me explain the components of this expression. So by eta mu, I mean take a unit normal vector to your sphere. So then, so J mu was the current, conserved current. So then you can contract this to get a local function on your sphere, which you can integrate over the sphere. And this I alpha is coming from this I alpha. So this I alpha is simply telling you which group element we started with. Okay, and this quantity, this is usually referred to as charge, right? Charge for this transformation defined on this sphere. Now, so what will be the outcome of this operation? So the idea is that this S3 with this current integrated over it acts on the local operator enclosed by this S3. So the final result is that this is equal to e to the power I alpha k phi to k. Right? So here, basic idea is that, so each phi has charge 1, and we have k copies of phi, so we have e to the power alpha. So k here is the charge of this operator. And so this is how I'm going to think about elements of my symmetry group acting on the operators of my theory. So in this case, U1 is acting on local operators. All right. Everything's clear so far? Okay. Now, so next, I'm going to call this a zero-form symmetry. And this 0 refers to the dimension of my operator, or the dimension of the support of the operator. So this operator is supported at a point in spacetime, which is 0-dimensional, hence the name zero-form symmetry. And the claim that I'm going to make is that the existence of a zero-form symmetry implies the existence of topological operators of codimension 1. Let me explain the terms. So zero-form symmetry, as I mentioned earlier, some symmetry that acts on operators separated at points. Topological operators means that if you deform the support of these operators smoothly, nothing is going to change, in the sense that if you inserted two operators in a correlation functions that are related by smooth deformation of their support, the correlation functions are going to be invariant. An example of such an operator is, of course, this operator, this integration of your current over S3. As I was saying earlier, that as long as it's topologically an S3, the exact geometry doesn't matter. You can deform it to be S3 and ellipsoid or whatever. It's going to do the same thing. So this is an example of a topological operator tied to the existence of the zero-form symmetry. And codimension 1 means that the dimension of the operator is 1 less than the dimension of the spacetime. So here I said that I have 4-dimensional spacetime, and this operator was 3-dimensional, hence 1 codimensional. Right? So this is just an example of this claim, which I say is more general. So whenever you have a zero-form symmetry, you have topological operators of codimension 1 associated to them. And they are always going to be constructed in this way, that you would take your current, which is going to be a 1 form, or, well, it's a vector field, but you can construct a 1 form out of it. And then, well, let me write down the construction. So what does zero-form symmetry mean? So from zero-form symmetry, using Noether's theorem, you always have a conserved current, right? So for example, so associated, so U1 was the group of zero-form symmetry transformations. So any element from U1, in this case, is a particular transformation, and associated to each particular transformation, you have a current. So let's say that you take such a transformation, associated to that you have this current J mu, and Noether's theorem tells you that this current is conserved. Again, so in this particular example, this was the explicit formula of the current in terms of the fundamental fields of my theory. And this was conserved by equations of motions, as you can check, right? Because this is, so what it's just the Laplacian acting on phi, which is the equation of motion from here. But more generally, even if you don't know what the Lagrangian is, simply the existence of the symmetry tells you that you have a current, which is going to be some non-trivial function of the fundamental fields, and it's going to be conserved by equations of motion. Okay. Now, when you have such a one-form field, such a vector field that's conserved, everything all right? You can define a one-form as follows, right? So this is a one-form. Is this notation familiar, or? Okay. Well, I mean, I'm sure some of the videos familiar, but please tell me if it's not. Okay. So what can I do with this one? So for you can take the hot star. Right? This is a d minus one form, where d is just dimension of the spacetime. Right? Well, I mean, if this is not familiar, just believe me that there is an operation that if I give you a p form where p can be anything, this canonically constructs a d minus p form. So for a one form, you have a d minus one form. Okay. Now, any d minus one form, you can integrate over any d minus one dimensional submanifold over spacetime. So in this case, we integrated something over S3, So similarly, so let's say that M d minus 1 is a d minus 1 dimensional submanifold. And I'm going to take it to be closed. Closed means that this submanifold doesn't have any boundary. So for example, this NH3 doesn't have a boundary, right? But if you take H3 and cut a hole out of that H3, so then it does have a boundary, which is where you cut your hole. Let's consider only submanifolds that don't have any boundaries. So then you can integrate the star J over this closed submanifold. And my claim is that this is a topological operator. So here, topological means that if I deform this closed submanifold smoothly, this operator is not going to change. So let me give this operator a name, and let me call it supports MD minus 1. So when I said it's topological, I mean that if I have I'm computing some kind of correlation function where I have inserted this operator, and I have other operators, they can be whatever. Then this correlation function is going to remain invariant if I change the support of my operator. So instead of MD minus 1, I can take M tilde D minus 1, where M tilde is a smooth deformation of M. So here you had this S3, you kind of put a dent somewhere in the S3. So that's a smooth deformation. There are some caveats, which is that, so here I have other operators located at different points in my spacetime. So when I'm doing this deformation, I just have to make sure that I am not hitting any of the other insertions of operators. As long as that holds, this correlation function is not going to depend on the support. That's what I mean by this operator being topological. Okay, so now why is this true? Let me first quickly say why it's true, and then maybe I'll elaborate a bit more. So let's look at this operator. It was star J integrated over MD minus 1. Now, so suppose, let's say this is a picture of MD minus 1. Okay. I'm not really specifying what D is or what MD minus 1 really is. This is just a cartoon. So imagine that this picture represents MD minus 1. And suppose that this is M tilde D minus 1. And when I say that this is a smooth deformation of this, it means that you can smoothly move this around and deform it so that it becomes this. In other words, there is a d-dimensional submanifold connecting this whole thing. Maybe you can call it ND, such that ND has two boundaries. One is this MD minus 1, and the other is M tilde D minus 1. Now, if you want an example of this phenomena, you can take this picture literally, in which case MD minus 1 is literally this closed loop, and M tilde D minus 1 is literally this closed loop. And one is a smooth deformation of the other because I can draw a cylinder such that it has two boundaries, the two boundaries being these two closed one-dimensional manifolds. But of course, this kind of picture holds in general. Now, if I want to prove that this operator doesn't really depend on the support, it can be MD minus 1 or M tilde D minus 1. I can do it as follows. So what is the difference between this and can you remind me when I have maybe 15 minutes left? So this difference is going to be the extra derivative acting on star J and integrated over ND. Right? So this is just Stokes theorem. Are you familiar with this kind of formulation of Stokes theorem? Okay, great. So the point is that the integral of an exact form over a manifold is equal to the integral of the form itself over the boundary of that. And there's a sign because they're two different boundaries at different orientations. And so now we use Noether's theorem, because if you break down what this looks like in terms of components, it's going to look like precisely the divergence of your current, and then the volume form, which will look like something depending on how many coordinates you have and so on and so forth. Well, if you're in d dimensions, maybe you have something like this. So dx1 and dxt. Okay. And we know that the current is conserved. So this is 0. In other words, so this is 0. So these two things are exactly the same. Hence my claim that this operator is topological. Okay. Make sense? All right. Now, this argument is fine, except it's very classical. So as I was saying earlier, that if I'm actually computing a correlation function in my quantum field theory, then when I'm doing this kind of deformation, I have to worry a little bit about there being other operators inserted here. And so that I don't, when I am deforming this operator by smoothly moving to this thing, that I don't hit any of these other insertions. But what happens if I do have other insertions? So let me look at an example. Suppose I will draw some very simplified picture. Suppose this is this line is my MD. Okay. Actually, you can imagine that maybe this line goes on and takes some complicated shape. But I'm looking at a particular part of this line. It's MD. And suppose I want to deform this line to another line, M tilde D. And of course, remember that I have integrals of currents over this thing. I have an integral of current here. I have an integral of current here. You can see this. Fine. If there are no operators in between, it's fine. I can just do it. But if there is an operator somewhere here, maybe I have an operator here, then of course I cannot smoothly move this line over to this one, right? At some point I'm going to hit this line. What I can do, however, is that I can move this line, say, up to here, just avoiding this operator by a little bit. So while I'm moving this line to here, I'm not intersecting any other operator. So this argument holds. And integral of my current over this line is the same as in the integral of my current over this line. Let me divide this line into 3 parts. Should give some names. Let's say so A1 is this segment, C1 is this semicircular segment, and A2 is this vertical segment. And it's clear that the operator defined on this line is the same as the operator defined here. And similarly, the operator defined here is going to be the same as the operator defined here. Right? Because again, going from here to here, there are no local operators on the way. Okay. Similarly, B1 is this segment, B2 is this segment, and C2 is this segment. So now, suppose I want to compare the operator defined here with the operator defined here. So what can I say? So clearly, this integrated over MD, I think it was D-1, sorry. Is the same as the integral over A1 plus integral over C1 plus integral over A2 of the same star J. And similarly, this operator is integral over B1 plus C2 plus B2 of star J. If I take the difference, I'm not writing the D minus 1, it's always there. Now, so you can imagine that, so I can bring these two lines arbitrarily close, and similarly, I can bring these two lines arbitrarily close. So at the end of the day, the integrals over A1 and B1 are going to be the same, and the integrals over A2 and B2 are going to be the same. So what I'm going to left with is the difference between the integral over this and the integral over this. So when you're taking difference between integrals over two lines, that just means that you can take the sum by reversing the orientation for one of the segments, right? So here what you find is that this was the difference between C1 minus C2. In other words, it's a closed integral over this segment. Of star J, right? So what's happening here is that I have a topological operator defined here, and I have a local operator here. So this is the same as moving my topological operator to the other side, but also introducing a closed integration around my local operator, right? Okay. Now, so what is the integral of your current on a closed surface enclosing a local operator? Any ideas? Well, this is what we started with, right? So we were saying that, so how does a symmetry act on your operators? You take your current and you integrate it over a closed surface surrounding a local operator. And the result is the action of the corresponding symmetry transformation on your local operator, right? So what we have here is that if I move a topological operator associated to a transformation across a local operator, that's fine, as long as you transform the local operator according to the action of that symmetry transformation, right? So this is going to be some group element corresponding to the current, right? So the current comes from the conservation of a symmetry transformation, and here by G, I simply am referring to that symmetry transformation. So G acting on a local operator in however way it acts, that depends on the theory, of course, plus the original operator. Now move to the other side, right? Okay. So far the picture that I'm trying to paint is that, right? So here I simply started from the assumption that I have a conserved current. Now, you have a conserved current when you have a symmetry in the theory. A symmetry is some kind of transformation that acts on the fields of the theory or the local operators of the theory. So here, by G, I am simply referring to that abstract transformation that acts on the local operator O here, right? Because since you have a current, you have some transformation, right? And whatever that is, I'm calling it G for now. All right. Okay. So what have I said so far? So I've said that if you have a symmetry that acts on the local operators of the theory, then you have a one-form conserved current. In other words, you have one codimensional topological operators in your theory, which you can freely move around without changing the correlation function. But if you ever hit a local operator, you simply transform that local operator according to the transformation that corresponds to that topological operator, right? Because remember that each topological operator comes with a current, which comes associated to a transformation. All right. So, any questions so far? Yeah. Yes. Yeah, good question. Let's see. So let me draw a picture first. Suppose you have two operators, right? You have O1 and O2, and you have some topological operator. And you want to move this to the other side. So from what I have said so far, the only thing that you can conclude is that you can move this here by putting something here, right? And this integrated operator surrounding this pair of local operators, the only thing that I can say definitively is that this is going to transform these two local operators according to the symmetry that exists in your theory. Now, how that symmetry acts, it may act linearly, it may act non-linearly. That you cannot entirely tell. For that, you need to look at the theory itself and how the symmetry is realized. So this is simply abstractly the transformation acting on the operators in however way it acts. This does not rely on any particular information about the dynamics or anything else. Okay, but most of the cases that we will encounter now or later is going to be linear action. All right. So we have established, I hope, that zero form symmetry is the same as codimension 1 topological operator. Okay, so zero form, remember that it means transformations that act on local operators. All right. Now, there are different ways of figuring out what a noether current looks like in terms of the fields of your theory. If I give you a Lagrangian and some transformation, maybe the one that you first see in the textbook is that you vary your action, something like this. So where you take the Lagrangian, you consider the variation of the Lagrangian, and you have something proportional to the equations of motions plus some total derivatives, right? So something of this form. And so from here, you kind of read off what this conserved current is. But another way that you can derive the form of this conserved current is the following. Yeah, well, so maybe you're familiar with this kind of procedure for determining what the current looks like, right? All right. If not, that's okay. What I'm going to say is that one perspective on symmetry, on global symmetry. Okay, so maybe I can distinguish between global and gauge symmetry. So because, yeah, in textbook, they're all referred to as symmetry, and sometimes the distinction is clarified, but sometimes maybe not. Gauge symmetry is not a symmetry of your theory, right? It's a redundancy of your description. The same physics may have different descriptions, and those different descriptions may have completely different gauge symmetry. So again, that's because gauge symmetry is not part of the physical information. So when I say, every time I say symmetry, I always mean global symmetry, unless I explicitly say gauge symmetry. Okay. So if you have a global symmetry, then you can think of, well, so you can kind of define the existence of the global symmetry as the ability to couple your theory to a background gauge field. Does that statement make sense? Okay, so let me give an example, and then maybe I will elaborate a bit. So let's take this example that we started with. So complex scalar. Complex scalar. So this is the Lagrangian. And yeah, it's clear that this has a global symmetry, a U1 symmetry. Now, you can also couple this theory to a background gauge field. What I mean is that you can replace these derivatives with covariant derivatives. Right, so you can change your Lagrangian to this. And when I write this, I do not mean that I have introduced a dynamical gauge field. The distinction between dynamical and background fields is that in your path integration, you integrate over the dynamical fields, but the background fields are some constant values. Okay? You do not integrate over them. So here, for example, you would have something like this as the action exponentiated, and then you would have a path integration. And the path integration still only consists of d phi and d phi bar. There is no dA. Yeah. That depends on whether you take AT Hermitian or anti-Hermitian. I'm not going to worry too much about I's or 2's or H bars. Okay, so this is what I mean. So here, why can we couple this theory to this background connection? Because we had this U1 symmetry. I mean, if this is the first time you are seeing this statement, then just take this example as a motivation. That whenever you have a global symmetry in your theory, you can introduce these background fields by changing your derivatives to covariant derivatives. Okay. What it really tells you is that, so you have a symmetry, meaning that you have the well-defined action of maybe some group on the fields of your theory, and coupling a background connection means that you are kind of changing the prescription of how to identify local operators located at different points. I mean, you can move operators from one place to another. If there is no background field, the same operator goes from one place to another. But if there's a background field, you have a connection, so you parallel transport according to the connection. Right? Okay. Another example of background field may be that suppose you have QFT on R4, which is you often study, maybe R4 or R1, 3, so the Minkowski space. But you can imagine that maybe you want to study the theory not on flat space, but on curved manifold. Our universe may be a curved manifold, right? That may have some non-zero curvature. So then it may be well motivated to study quantum field theories on curved spaces. So what does it mean to go from flat space to curved space? It simply means that your original theory, if it was written in a coordinate invariant way, then it has a global symmetry, which the coordinate invariance, and you can couple it to background connection, which in this case happens to be the metric. So you simply plug in the metric at right places, right? And that gives you a classical action of your QFT in a curved space. Anyway, the whole point is that if you have global symmetry, you can couple it to background connection. And yeah, the reason that I'm saying this is that, so one way to derive what the Noether's current look like for a given global symmetry in your theory is to couple it to background connection, such as this, and then expand it. So break down this product into sums, and then look at the terms that are linear in the connection, and the coefficient of that term is going to be the current. So if I expand my Lagrangian, well, the first term is what it was before, right? And then the next term is going to be a mu. Yeah, and you can kind of see that it's going to be actually, maybe this example is not very clear. Let me modify this statement slightly. In a first order formulation, so first order formulation means that your Lagrangian is going to be linear in derivatives, not quadratic. So this is quadratic, right? So we have two derivatives. So in a first order formulation, you declare the derivative of one of the fields to be a new fundamental field, so that this action will look like some new field, and then so maybe the original field. And of course, you will have the complex conjugate term of this as well. So you will have psi bar del mu. Well, in this case, this is going to have also an index, something like this. Right? So this is analogous to going from Lagrangian formulation to Hamiltonian formulation. Okay, so this is in some classical mechanical stuff. So recall that Lagrangian is a function of your coordinates of your fields and derivatives of your fields, whereas Hamiltonian is only function of coordinates and momentum, right? No derivatives. So you reduce the number of derivatives by 1 when you go from Lagrangian to Hamiltonian. So this is called the first order formulation. And in first order formulation, the action always has this form that it looks like P, the momentum, dq. So some field that's canonically conjugate to some other field and one derivative in between. So here, for example, you had psi and you had derivative and you had fields. And in this formulation, the way that you determine the currents, the Noether currents, is that you replace the derivative with A. And this gives you something like this. And this PQ is going to be the Noether's current. Okay, so this is extremely schematic. So the reason that I am saying this is the following. You should be able to write down a term in a Lagrangian involving the Noether current and the background connection. That's what I wanted to say. So, when you have a zero form symmetry, as in this case, so the background connection is going to be an ordinary connection, so something like a mu. And you have a conserved current, which also has a single index, right? Because it's a vector, j mu. So by contracting them, you have a scalar, which you can integrate over your spacetime to write down a term in a Lagrangian, right? Great. Now you can imagine generalizing this thing and generalizing in the following sense. So instead of having a one-form connection, you can have a two-form connection. So it's some field some antisymmetric field that has two indices. Now, if you wanted to write down a term involving this two-form connection and something else, that something else will also need to have two antisymmetric indices, right? Then you can write something like this. So, okay, here you can ask several questions. So first question may be that why would you want to have some two-form field and want to think of it as generalization of a one-form connection or one-form gauge field? The answer to that is going to be a bit out of the scope of today's talk. But if you have studied string theory a bit, you're already kind of familiar with some gauge fields like this. So in string theory, there's something called the B field, which is a background gauge, which is a gauge field, have a dynamical background, and it is a two-form. So that's one example of when something like this happens. But if you have not studied string theory, then it's a bit hard, I guess, to motivate why you should study something like this. So maybe you're just playing with all possibilities. The next question that you can ask is, so here I said that the Noether's current associated to a conserved symmetry can be read off from the term that you get by coupling your theory to a background gauge field. Does that remain true if you have higher form gauge fields? So again, it's not obvious that it's true, but it happens to be true. But assuming it is true, and again, let's say that you're kind of playing with all possibilities. So what do you see here? So here, then you have a two-form gauge field and a two-form current. It's no longer a vector current, right? Now it's a tensor current. So when you had a vector current, so you could integrate that current over a one codimensional submanifold surrounding a point, and that would give you the transformation of the local operator at the point. So what happens if you have a higher form current? What kind of object does it act on? Okay, so let's take everything I'm saying on this page as some very vague motivation, because this may sound a bit esoteric. I mean, yeah, it's a legitimate question to ask. Why would you do this? Right? So yeah, let's say that these are some very vague motivations. But at the end of the day, what I will say is that the final statement will be that we can generalize this line, this zero form symmetry codimensional one topological operator, to the following. P form symmetry and codimension p plus 1 topological operator. Okay. Now let's look at what it means. Zero-form symmetry were transformations acting on zero-dimensional or local operators. So p-form symmetry should mean that it's some kind of transformation that acts on p-dimensional operators, not local or anything else, right? Okay. Codimension p plus 1, that's easier to understand. So suppose in three-dimensional space, if you have a closed line, that's topological in the sense that whatever you are doing with that line doesn't depend on the exact geometry of the line, but you can move it around, you can deform it. Then that line is topological. So it's a one-dimensional topological line in three-dimensional space. So it's codimension 2 topological line, right? So that's what this part is going to mean, that instead of having this kind of S3 in four-dimensional space, you would have an S2 in four-dimensional space if it's codimension 2, or S1 in four-dimensional space if it's codimension 3, and so on. But what are these things? So what are these extended objects on which these higher form currents are supposed to act on? So instead of trying to make this kind of motivations very rigorous, let me give you an example where this actually happens, and an example that you should all be familiar with. Let us consider four-dimensional Yang-Mills theory, or also called Maxwell's theory. This is just standard electromagnetism. And so what is the Lagrangian formulation of this theory? So you write down a four-dimensional action, d for d for x, and the curvature, something like this, right? You're all familiar with this Lagrangian? Okay. Yeah, and just to be sure that this f mu nu looks something like this, where this is the vector potential or something, right? It's the four-dimensional engagement. All right, let's consider this theory. I'm going to assume that you're all more or less familiar with what this is, right? It's the theory of electric charges, photons moving around, and so on and so forth. So my claim is going to be that this theory, in fact, has a higher form symmetry. So I was talking about p-form symmetry. So this theory has a one-form symmetry, which is already higher form, right? Because one-form symmetry is supposed to act on operators that are one-dimensional, not local operators. So actually, before I talk about operators, what are the local operators of this theory? Any guesses? Mu? That's true. Technically, yes. But you may object a little bit that mu is not a gauge invariant object, right? Because it transforms non-trivial under gauge transformation. And if something transforms non-trivial under gauge transformation, it's not a physical, I mean, it may have some physical information in it, but all of it is not going to be physical. Because whatever changes under gauge transformation must be non-physical, because gauge transformation is a redundancy. So yeah, of course, there are physical information in mu, but mu itself is not a physical observable unless you do gauge fixing. I will not go into details of gauge fixing, but okay, there are some ways of dealing with that. Something gauge invariant that you can try to write down is simply anything that you can, any Lorentz invariant operator that you can write down with f mu nu. And so one of the local operators is, of course, the Lagrangian itself. This is a local operator. It's gauge invariant, it's Lorentz invariant. So this is an operator. And similarly, you can try to write down higher powers of x. Okay, whatever. But these are not the most interesting operators in the theory. So what are the most commonly studied operators in a gauge theory? Or in this case, for example. You have all seen these operators, I'm 100% sure. Sorry? Rotation? Well, that's a transformation, right? But I mean, if you were computing the expectation values of some operator in the theory, what kind of operators would you want to compute expectation values of? Sorry? Time order? All? Well, I mean, yeah, you can compute correlation functions of these kind of things, or powers of these kind of things. But really, I think most of the times you would really study correlation functions of line operators. Say a Wilson line, right? A Wilson line is simply an observable that looks like this, integrated over some curve, right? So you take some line in your spacetime, gamma, and you integrate your gauge field over this. And if you exponentiate it, yes, again, you may need to put some numbers in front of these things to make it well defined. But yeah, so this is a non-local operator, right? Because it's defined on a line. It's not a local operator. And you have studied these things even if you haven't written down this formula, because you have studied the properties of an electron in your theory, right? You have studied what is the electric field created by an electron. So when you're solving the problem, what are you doing really? So what is an electron in this theory? So this is the Lagrangian, this is the action for my Yang-Mills theory, right? So this action does not have any field corresponding to an electron. It only has a field corresponding to, well, it's the gauge field. So when you're studying an electron in electrodynamics, in classical electrodynamics even, so what are you studying? I mean, what is an electron in this theory? Can I define an electron in this theory? I mean, as an observable, how would you describe what an electron is? Let's try to remember what kind of problems you studied in your undergrad. So you have an electron in your theory. Maybe you're trying to compute some kind of scattering. So an electron is creating some potential, and then you are maybe scattering some other charged particle that comes in into that potential and goes out in some direction, and you're trying to figuring out cross section or something. Right? So when you're doing this kind of computation, you are assuming this is kind of an undergrad class. You are assuming that the electron that sits at the center, that is responsible for scattering other particles, is not moving, right? The field that it's creating is static. That field is not being modified by the incoming and outgoing of other charged particles. So here, that electron that you're studying, it's not really a dynamical field in this Yang-Mills theory. It's because a dynamical field is something that is affected by what's going on around it. The electron is not affected by what's happening around it. So the electron is simply a source for the gauge field. In other words, sometimes people call it a heavy particle. It's so heavy that it is not moved by the moving around of other particles. It's infinitely heavy. Similar to how you treat the sun when you're solving the Kepler's problem, right? You are simply solving for the trajectory of planets around the sun. You are not trying to figure out how the sun deviates because of the gravitational field of the planet, right? Because the sun is heavy. Similarly, people use the same terminology. Of course, an electron is not particularly heavy, but an electron that is not affected by other charged particle is called a heavy charged particle or heavy electron. It's also called a probe particle, right? And the realization of such a probe particle in the QFT language is precisely a Wilson line, okay? Because a Wilson line, when you're defining it, you're specifying the trajectory of the line. So this gamma is fixed. If you have other dynamical particle being created or annihilated in your theory, the gamma is not going to change, okay? So, and if you add this operator to your Lagrangian, so if you have a Wilson line and you're computing correlation functions of the Wilson line, so what are you going to do? So you are going to integrate over dA, right? And you have your Yang-Mills action. I'm just going to write f squared. And then you have your Wilson line. Integration of A over the line operator. Now, okay, so let's see. So for the moment, let's imagine that I don't have this line operator. 15 minutes, okay, great, thanks. So for the moment, that imagine that I don't have this line operator. I just have the usual Yang-Mills action. So if you figure out the equation of motion of this Yang-Mills action, so what would you get? You would just get the usual Yang-Mills action without any source, right? So what are those things? Something like this. And I guess something like this, right? And in terms of differential forms, you can say that this is d star f equals to 0, and this is df equals to 0, right? You have seen this equation before. Okay. So these are the usual equations of motions without sources. So there's nothing here. Now let's put a Wilson line. So what will happen to the equations of motion? Well, so how do you derive equations of motions? You can put this inside here, right? You don't have to write E1 again. So you can think of the addition of the Wilson line as a modification to your action. But this modification is only supported at a line. Okay. So now if you vary this whole thing with respect to A, you are going to change one of these equations. And okay, so let me now remember which one, because I always forget. Does anyone know which one? Okay, I'm going to guess that it's the first one, but here I may be wrong. So you're going to modify this equation by, I'm not going to be very precise, but by delta function. In other words, d star f is still pretty much 0, except where the line is located. There it's not 0. Here it has some kind of singularity. More importantly, so if you solve this equation instead of this one, so the one with the Wilson line, you will find precisely the electromagnetic field created by a static charge and a static electric charge. So from there, you conclude that the addition of this Wilson line is the same as introducing a static charge in your theory. Okay, great. So the reason that I was saying all this is that this is a theory where you have line operators. Okay, so the line operators and possibly even higher dimensional operators are completely natural thing to study, and they appear in even the most basic theories. All right, so if you have local operators and if you have line operators, then it's very natural to consider symmetries or symmetry transformations that act, maybe some of them act only on local operators. Maybe some of them only act on line operators, right? And there's a reason why you shouldn't have symmetry that only transforms the line operators and doesn't do anything to local operators. I mean, why wouldn't you have them? Right? Because you are perfectly happy with having transformations that only act on local operators. Similarly, if you have line operators in your theory, you can have symmetry acting on line operators. And that's another way to kind of motivate why you should have generalized symmetry or higher form symmetries. Because it's perfectly natural to have extended operators in your theory. You can have local operators, you can have line operators, you can have operators defined on surfaces. So then it's also natural to consider symmetry transformations that act on operators of various dimensions. And in this particular example, we indeed have this kind of symmetry. In this Yang-Mills theory, we have one-form symmetries that act on these line operators and not on the local operators. So recall, so what was our criteria for having a zero-form symmetry? The criteria was that you have a vector field J, which was conserved. What is the most straightforward generalization of this if you want something that acts on a line operator? Okay. Actually, before I find the generalization. So when I was talking about symmetry transformations on local operators, so I had a point in, say, 4-dimensional space, then the charge or the transformation or the operator that generates transformation of this local operator, it was a sphere, right? Because you need a sphere to surround a point in any dimension. You need a 3-sphere to surround a point in 4 dimensions. So this was an S3. But if I have a line in 4 dimensions, so what do I need to surround this line? An S2. Is it clear why it's an S2? So my claim is that this has to be an S2. Okay. If it's not familiar, then think about it. It's just a matter of mental gymnastics. So the point is that if you have a d-dimensional operator, maybe p-dimensional operator in d-dimensional spacetime, you need a d minus p minus 1 dimensional operator to surround it. All right. So here are the important numbers: p and d minus p minus 1. Okay, so you can kind of figure it out later. So in four-dimensional Yang-Mills theory, if you have a line operator, you need a two-sphere to surround this thing, right? So here we integrated this star j over this. So j was the one form, the star j was a three form, which I could integrate over this thing. So what do I need here? So I need something that is a two form that I can integrate over S2, right? And so here recall that star j was closed, d star j was closed. D star j was 0 because of the Noether's theorem. So here I need something such that d of that something is 0. I need something here such that d of this something is 0. All right. And so if you write this kind of thing in components, you will find this del mu something nu rho epsilon mu nu rho sigma equals to 0. And of course, we have a candidate for that already. It's f, right? Because df equals to 0 is one of the equations of motion of the theory. Well, actually, it's a Bianchi identity. So in fact, from Yang-Mills, you get two equations. So you get d of f equals to 0 and d star of f equals to 0. So you can integrate f over an S2. That will give you something topological. And you can integrate star of f over S2. That will also give you something topological. So what does it mean? It means that in four-dimensional Yang-Mills theory, you have two-dimensional topological operators, right? You have two different kinds of topological operators. So let me call, say, Q E. I will explain the E later. So let me define these as S2 integration of star F over S2 and QM S2 integration of F over S2. Here there are some numbers that are actually important. I think the most important part is that so this I think involves the electric coupling constants. Let's say E squared, and this coupling constant appears also in the Lagrangian numbers. Actually, anyway, I'm not going to worry too much about what other numbers appear here. Okay, so we can define these two operators in our Yang-Mills theory, and both of these are topological. This is topological because df equals to 0 by Bianchi identity, and this is topological because d star f equals to 0 by equation of motion. Now, if you have a topological operator, does it automatically give you a symmetry of the theory? Well, it does if it acts non-trivially on something, right? Because you can say that you have a symmetry of a theory, but that symmetry acts trivially on everything, meaning that it doesn't change anything of the theory. Okay, of course, it's a symmetry, but it's a symmetry that doesn't mean anything. It's trivial. So the question is, do these things act non-trivially on anything? Are there any operators in your theory, and they have to be line operators, that are charged under these charges, right? So what does that mean? So recall that, so how did we compute the action of a symmetry generator on a local operator? So it was here. So we integrated this charge operator. So recall that this is a charge operator around the local operator. And the result was the transformation of the local operator by the symmetry transformation. I think we had another example in terms of phi to the k. Where is it? I guess this one. So we had phi to the k at a point. We put a topological operator surrounding this local operator, and the answer was phi to the k with some transformation. So do we get something like this here? So suppose I have an S2 in 4 dimension, and I have this S2 surrounding some line operator, right? So the picture is going to be the same, right? So it's some S2. Suppose I have star F, and I have some line operator here. Okay, actually, maybe let me draw it slightly differently. So it's a line operator, and let me call this my S2. So what kind of line operators do I need to have here such that this integration surrounding this line gives me this line, but with some number here? this is also something that you have seen before. So what is this quantity? The integration of star f over an S2. Well, so maybe if I write it slightly differently. So recall that f, this electromagnetic tensor, stress tensor or something, I forgot what it's called. So if you write the components, it has this form, right? E or Ex, Ey, Ez or something, so where E is the electric field. Actually, is it this or? And then you have B's somewhere. Something like this, and zeros everywhere else. Okay, either this is F or star F. Anyway, the point is that the components of this electromagnetic stress tensor is written in terms of electric and magnetic field. And if you write this, I mean, if you boil this down in terms of its components, you will see that this is the electric field dotted with some volume form on your S2 integrated over S2. So what is this quantity? Yeah, and of course I have this E square here and A square here. It's the electric charge inside this S2, right? So it's electric charge. So what does it mean? It means that if this line carries electric charge, then this topological operator surrounding this line will give you the line back multiplied by e to the power electric charge. I'm almost done. Is it working now? Maybe I need to turn it on. Hello, working? I think it should be right now. Yeah, I'm almost done. It's okay. All right. So the last things that I was going to say is that if you have a line operator carrying electric charge, in other words, a Wilson line, then if you have this topological operator created using this conserved current surrounding this line, it's going to give you the line back multiplied by a phase depending on the electric charge carried by that line. So this line is charged under this operator. And recall that this is a two-form operator in the sense that I was using a two-form current to create this operator. So the statement here is that Wilson lines are charged under, okay, so what is the group of transformations that I have here? So I can put any complex number here, or any real number here, and I'm going to have the electric charge multiplied by alpha. So you have one parameter for this group. And in fact, okay, if you look at it a bit carefully, you can convince yourself that the group of transformations is, give you a copy of U1. It's in fact very similar to the U1 that we saw earlier. So for this scalar theory, for example. Yeah, it's almost exactly like this, right? Because you get the operator back multiplied by phase. So this was U1, and for these line operators, you also have a U1. Charge under U1. U1, but it's U1 one-form symmetry. Now, if this Wilson line, if instead of Wilson line, if you have a tooth line which carries magnetic charge, right? So it's a static magnetic monopole instead of a static electric charge. Then this will be zero because the magnetic monopole does not create any non-zero electric field. So the tooth lines are not charged under the Wilson, not charged under this U1 one-form symmetry. But of course, you also have these topological operators where S2 and you have integration of F, right? And recall that so if you break this down in terms of component, you have integration of S2, the magnetic field, and ds. So now if you have a magnetic monopole or a two line surrounded by this charge operator, then you're going to get a phase. So you have a two line, and you have, say, this operator surrounding this two line. So this is going to be the two line itself, multiplied by phase carrying the magnetic charge. Okay. So the statement from here is that two lines are charged under U1, but it's a different U1. So let me call this U1E because it for electric and U1M for magnetic. And again, this is a one from symmetry. So the point is that 4D Yang-Mills theory has U1 electric times U1 magnetic global symmetry. Global symmetry. And Wilson lines are charged under U1 electric, and two lines are charged under U1 magnetic. Okay. So even in this extremely simple theory of electrodynamics, you have higher form symmetry, in this case one form symmetries, that only act on the line operators of the theory. Okay, so this will be the formal end of the talk, but I will just make a few comments that, so what kind of things can you understand by studying these higher form symmetries? Well, so first thing is that you should study these kind of symmetries because they're there, right? They're as valid as symmetries as zero form symmetries of local operators. Because in most physical theories, you will have extended operators and there will be symmetries acting on them. If you kind of forget about them, then you're forgetting a lot of physical information. Another very good reason is that this way of thinking about symmetries in terms of topological lines moving freely in your space-time and inducing transformation when they cross other operators, this generalizes well for discrete symmetries. Because for discrete symmetries, you do not have gauge fields. So the way that you can couple a continuous global symmetry to background gauge field, we cannot do that for discrete symmetries. But you can still have topological lines, and you can define parallel transport by putting some networks of topological lines labeled by elements of a discrete group. Furthermore, it even generalizes to symmetries that are not invertible. So group-like symmetries are invertible because for any group element, you have an inverse element. So whatever transformation you do by one element of a group, you can undo it by another element of a group. But this picture of topological lines allow you to have lines that are not invertible. So you cannot, if you have a line topological operator, you cannot necessarily find another topological operator, which if you put on top of each other, they vanish. It may happen, it may not happen, and both are fine possibilities. So this picture allows you to have non-invertible symmetries that are not valid in groups, but will be valid in something called a fusion category. Furthermore, if you have studied condensed matter physics, then you probably know that it's very important to understand how symmetry breaks when you go to infrared to figure out what phase your matter will be in. And for most of history, people have studied the significance of zero form symmetries or symmetries of local operators to figure out phases of matter. They have studied which operators takes values, which local operator takes non-zero webs at IR and so on and so forth to figure out the pattern of symmetry breaking and the pattern of phase transition. But of course, as you're saying that in most of your physical theories, you will have extended operators and extended symmetries. So if you really want to figure out all the phases of matter, you should also figure out how these extended symmetries are broken in the IR. And for that, of course, first to understand how these extended symmetries are, what their properties are basically. Okay, so what is the point of my talk? There are extended operators. There are symmetries that act only on extended operators. These are called higher form symmetries. And you can generalize them to discrete groups or non-invertible groups, and they are important for phase transitions. I have only given you the very basic introduction, and please feel free to ask me any questions. Thank you.